Hello there, and welcome to Simple Sleepy Science. Tonight, we're drifting into the world of airplanes. Those metal birds that carry you through the sky. Right now, somewhere above your head, hundreds of people are floating 6 miles high, moving faster than a racing car, while they sleep, read, or sip coffee like they're sitting in their living room. Ever wondered what makes airplanes glide so smoothly through the sky? Let's relax together and discover how these flying marvels help even the busiest minds unwind. If this journey brings you calm, consider hitting that like button and subscribing to join fellow science lovers who drift to sleep this way. Leave a comment and let me know where you're listening from and what time it is there. It's wonderful knowing we're scattered across the world, all looking up at the same sky, sharing these peaceful moments together. Here's something that will change how you see every flight. When you're cruising at 35,000 feet, you're actually traveling through air so thin that if the cabin lost pressure, you'd pass out in about 15 seconds. But you never do, because wrapped around you is one of the most carefully designed safety systems humans have ever created. This is a place for calm curiosity, for drifting through the science of flight with wonder and peace. So settle in, get comfortable, let the weight of the day fall away. We begin with something you've never thought about, but should absolutely blow your mind. The air you breathe on a plane isn't really the air from outside. At cruising altitude, the outside air is thin, bitter cold at -60 degrees Fahrenheit, and contains so little oxygen that you'd lose consciousness before you could even realize something was wrong. Your brain would simply fade to black within seconds. No warning, no chance to react. So airplanes don't just fly through air, they carry air with them. They create a pocket of Earth's surface, 6 miles above the actual surface. Think about that for a moment. You're sitting in a metal tube, screaming through an environment that would kill you instantly, and yet you can breathe as easily as if you were sitting in your living room. You can read a book, take a nap, eat a meal, all because that tube is maintaining an artificial atmosphere around you. The cabin pressure system works by pulling air from the jet engines, not the exhaust, but air from the compressor section, where it's squeezed and heated. This bleed air, as it's called, is cooled down and pumped into the cabin continuously. At the same time, small valves release air at a controlled rate to maintain the right pressure. The system balances these two flows, incoming and outgoing, thousands of times per second. The pressure inside isn't quite the same as ground level. That would require too much stress on the airplane's structure. Instead, the cabin is pressurized to feel like you're at about 1,000 to 8,000 feet elevation, like you're in a city in the mountains. Denver, Colorado sits at about 5,000 feet. So, when you're flying, your body thinks it's in Denver, even though you're actually more than a mile higher than Mount Everest. This invisible bubble of breathable air follows you across continents, over oceans, through different time zones. It's pumped fresh every few minutes, filtered and recirculated. The air you're breathing at 35,000 feet is actually cleaner than the air in most office buildings. It passes through HEPA filters that remove 99.97% of particles, including bacteria and viruses. But how fast is that pocket of Earth actually moving through the sky? The answer is stranger than you think. When you're cruising at 35,000 feet, you're moving at around 500 to 600 miles per hour. That's nearly the speed of sound. A bullet from many handguns travels slower than you do when you're sipping ginger ale in seat 23B. Yet you feel nothing. No wind, no rush. Not even a hint that you're screaming through the atmosphere faster than any car on Earth could ever go. This seems impossible at first. How can you be moving that fast and feel completely still? The answer lies in something called constant velocity. Your body doesn't feel speed. It never has. What you feel is change in speed. Acceleration, deceleration, the push back into your seat when a car speeds up, the lurch forward when it brakes. But when speed is constant, when you're neither speeding up nor slowing down, your body has no way to detect the motion. Inside that airplane cabin, everything is moving at exactly the same speed. You, your seat, your coffee, the air around you, all of it traveling together at 500 miles per hour. There's no difference in velocity between you and your surroundings. No relative motion. It's like being in a car on a perfectly smooth highway. If you close your eyes, you can't tell if you're moving at 60 miles per hour or sitting still in a parking lot. But here's where it gets beautiful. The Earth itself is spinning at about 1,000 miles per hour at the equator. Right now, as you listen to this, you're already moving at twice the speed of that airplane, just from standing on the planet's surface. You've been doing it your entire life and never felt it once. Because everything around you, the ground, the air, the trees, is moving with you. The plane adds its speed on top of Earth's rotation. If you're flying east, with the spin, you're actually moving through space at over 1,500 miles per hour relative to the sun. But you feel none of it. You could balance a pencil on its tip on your tray table, and it would stay standing. The coffee in your cup sits perfectly level. A baby can sleep peacefully while traveling faster than the speed of sound. This is the magic of inertia. Objects in motion stay in motion unless something pushes or pulls on them. You and the plane are in motion together, moving as one unit through the sky. The only time you feel anything is during takeoff, when the plane accelerates from 0 to 180 miles per hour in about 30 seconds. Or during landing, when it decelerates back to 0. Or when turbulence creates small changes in speed or direction. That stillness you feel at cruising altitude, that sense of floating in a quiet bubble, is real. You are floating, not held up by anything solid, but by air pressure differences and forward momentum. The plane isn't sitting on anything. It's not touching anything except the thin atmosphere rushing past. And that atmosphere is so thin up there that if you stuck your hand out the window, the air would barely feel thicker than steam. All that power, all that speed, sustained by something you can't even see. Which brings us to the engines that create it, and they're far more remarkable than most people realize. A jet engine is essentially a controlled explosion that never stops. It sucks in air at the front, compresses it until it's incredibly dense, sprays fuel into it, lights it on fire, and then that explosion shoots out the back so violently that it pushes the entire airplane forward. And this happens continuously, thousands of times per second, for hours and hours without stopping. Let's break down what's actually happening inside that cylindrical pod hanging beneath the wing. Air rushes into the front intake, pulled by a massive fan with blades as tall as a person. That fan spins at around 3,000 rotations per minute, moving huge volumes of air. Some of that air goes around the engine core, but the important stuff goes inside, into the compressor section. The compressor is a series of spinning blades that squeeze the air tighter and tighter, making it denser with each stage. By the time air reaches the combustion chamber, it's been compressed to about 30 times its original pressure. Imagine taking a balloon full of air and squeezing it down to the size of a grape. That's what's happening to the air molecules. In the combustion chamber, fuel is sprayed into this super compressed air as a fine mist. Then, igniters, basically giant spark plugs, light it. The explosion is immediate and intense. Temperatures inside reach 12 to 2000 degrees Fahrenheit, hot enough to melt most metals. But the chamber is designed to handle it, cooled by air flowing along its walls. That explosion wants to go everywhere at once, expanding in all directions. But there's only one path available: backward, through the turbine section. These hot, expanding gases spin another set of blades as they exit. And those blades are connected by a shaft to the compressor and fan at the front. So the explosion itself powers the compression that feeds the explosion. It's a self-sustaining cycle. The gases then shoot out the back through the exhaust nozzle at over 1 million miles per hour. That's the thrust. That's what pushes the plane forward. Newton's third law in action. For every action, there's an equal and opposite reaction. The engine throws air backward with tremendous force, so the plane moves forward with equal force. What's remarkable is how reliable this controlled violence is. These engines run for thousands of hours between major maintenance. They operate in temperatures ranging from 130 degrees on a desert runway to -60 at cruising altitude. They handle rain, snow, ice, dust, even the occasional bird strike. And they almost never fail. Modern jet engines are also surprisingly efficient. Most of the thrust actually comes from that big fan at the front, not the combustion. The fan pushes air around the engine core, and that bypass air creates most of the forward push. It's quieter and uses less fuel than pure jet thrust. The explosion inside is really just there to power the fan. Each engine produces about 30,000 to 40,000 pounds of thrust. To put that in perspective, that's like having 30,000 people all pushing on the plane at once. And most airplanes have 2 or 4 of these engines. All that power, all that force, concentrated into moving one metal tube forward through thin air. Yet the wings barely move, barely flex, because wings aren't what you think they are. Here's the beautiful secret of wings. They're shaped so that air traveling over the top has to move faster than air traveling underneath. Faster air creates lower pressure above, higher pressure below. And that difference, that gentle push from underneath, lifts hundreds of tons of metal into the sky and keeps it there, effortlessly, for as long as the plane keeps moving forward. This is called the Bernoulli principle, named after an 18th century Swiss mathematician who figured out that fast-moving fluids create less pressure than slow-moving fluids. Air is a fluid, and when a wing cuts through it, the air splits. Some goes under, some goes over. The top surface of the wing is curved, longer than the flat bottom. Air traveling over that curve has farther to go in the same amount of time, so it speeds up. That speed difference creates a pressure difference. The air below pushes up harder than the air above pushes down. The result is lift. Invisible hands holding the plane aloft. The faster the plane moves, the more air rushes over the wings, the more lift is generated. This is why planes need to reach a certain speed before they can take off. Below that speed, there isn't enough lift to overcome gravity. But there's another factor at work. The wing isn't perfectly flat. It's angled slightly upward, tilted into the oncoming air. This angle of attack means the wing is actually deflecting air downward as it moves forward. Push air down, and Newton's third law pushes you up. So lift comes from two sources working together: pressure difference and air deflection. Physics and geometry combining to make the impossible routine. The wings on a large passenger jet can generate over 400,000 pounds of lift at cruising speed. That's enough to hold up not just the plane's weight, but also hundreds of passengers, their luggage, thousands of gallons of fuel, and all the food, water, and equipment needed for the flight. All of it suspended by nothing but moving air and cleverly shaped metal. And those wings are flexible. They're designed to bend. If you watch during takeoff, you'll see the wingtips flex upward as lift increases. On some planes, the tips can move up or down by several feet. This isn't a flaw, it's intentional. Rigid wings would crack under the stress of turbulence and shifting loads. Flexible wings absorb the forces, distributing stress along their length instead of concentrating it at weak points. Inside each wing is a complex structure of spars and ribs, like the skeleton of a massive bird. Fuel tanks fill much of the interior space. Hydraulic lines run through them. Electrical cables. Control surfaces along the trailing edge. Flaps and ailerons that can change the wing's shape and angle. All of it working together to create and control lift. The wing doesn't just hold the plane up, it holds it steady. The slight upward angle, called dihedral, helps the plane resist rolling from side to side. If one wing dips, it meets the oncoming air at a sharper angle, creating more lift on that side, pushing it back up. The plane naturally wants to fly level. But what happens when the plane needs to stop moving forward, when it needs to slow down while still in the air? The answer requires destroying everything that makes a wing work. In a car, you have brakes that squeeze your wheels. In an airplane, 6 miles up with nothing to push against, slowing down requires something different. Pilots deploy spoilers, flat panels that pop up from the wings, and intentionally destroy the smooth airflow that's keeping you aloft. They create drag, turbulence, resistance. The plane pushes against air like you'd push against water in a pool. Watch the wings during descent, and you'll see them transform. Panels rise up from the top surface, breaking that carefully shaped curve that creates lift. The smooth flow of air becomes chaotic, tumbling and swirling instead of streaming cleanly over the wing. This chaos is exactly what the pilots want. It increases drag dramatically, helping the plane lose speed and altitude without the engines having to work as hard. There are different types of drag working against a moving airplane. Parasitic drag comes from the plane's shape. Every surface that isn't perfectly smooth, every rivet and antenna creating tiny disturbances in the airflow. Form drag comes from the plane's overall shape pushing through air. And induced drag comes from the wingtips, where high-pressure air below tries to curl around and equalize with low-pressure air above, creating spiraling vortices that trail behind like invisible tornadoes. Spoilers amplify all of this. They make the plane less aerodynamic on purpose. Some spoilers are small, used for fine adjustments during cruise. Others are large panels that rise up dramatically, cutting lift by as much as 60%. On landing, they deploy fully the moment the wheels touch down, forcing the plane's weight onto the tires so the wheel brakes can grip effectively. But spoilers aren't the only way to slow down. Flaps, those panels that extend from the trailing edge of the wings, serve a dual purpose. During takeoff and landing, they increase both lift and drag. Extended flaps change the wing's shape, making it more curved, creating more lift at slower speeds. This lets the plane take off and land at speeds low enough to be safe. But they also create enormous drag, helping the plane decelerate. Speed brakes are another tool. These are spoiler panels that can be deployed symmetrically on both wings during flight, creating drag without affecting the plane's balance or attitude. Pilots use them when they need to descend quickly without gaining speed, or when air traffic control tells them to slow down while still at altitude. Think about the precision required here. The plane is traveling at 500 miles per hour. It needs to slow to about 150 miles per hour for landing, lose 6 miles of altitude, and arrive at exactly the right spot on the runway at exactly the right moment. Too fast and it overshoots. Too slow and it stalls. The pilots are constantly adjusting, using spoilers, flaps, and engine thrust to control their descent rate and speed. And here's something most passengers never realize. When you feel the plane descend, that sinking feeling in your stomach, the plane isn't necessarily pointing downward. It might be flying completely level while losing altitude, using spoilers and reduced engine power to sink through the air. The nose doesn't have to drop for the plane to descend. When the plane finally touches down, there's one moment that every passenger hears, but nobody really understands. That roaring sound that fills the cabin, louder than the engines during takeoff. That roaring sound right after the wheels touch the runway isn't the engines working harder. It's the engines doing something remarkable. Massive panels called thrust reversers deploy, redirecting all that explosive power forward instead of backward. The engine's fury, which was pushing you forward at 500 miles per hour, is now fighting against your motion, helping you stop. Here's what's happening in those few seconds. As soon as the main wheels make contact with the runway, the pilots pull back on the throttle levers, activating the thrust reversers. Metal panels called blocker doors swing into position behind the engine, blocking the normal exhaust path. The hot gases that usually shoot straight out the back are now forced to redirect through vents that angle forward, roughly 45 degrees from straight ahead. All that thrust that was pushing the plane forward now pushes against its motion. It's like running full speed and then suddenly pushing against the ground to stop yourself. The effect is immediate and powerful. Thrust reversers can provide up to 50% of the plane's stopping power on a dry runway, even more on wet or icy surfaces where wheel brakes are less effective. The sound is incredible because you're hearing the full force of those jet engines unleashed without any muffling. During normal flight, the exhaust exits cleanly out the back, away from the cabin. But with thrust reversers deployed, all that noise is directed forward and sideways, bouncing off the runway, echoing around the fuselage. It's one of the loudest moments of any flight. Not all planes use thrust reversers the same way. Some have target-style reversers that redirect air from the bypass fan, the big fan at the front of the engine. Others use clamshell doors that close over the exhaust nozzle. A few older designs used bucket-style reversers that literally caught the exhaust like a catcher's mitt and threw it forward. Each design solves the same problem, but with different engineering approaches. Pilots don't always use full reverse thrust. On long runways with good weather, they might use minimal reverse to save wear and tear on the engines. But on short runways, wet surfaces, or in crosswinds, they'll use maximum reverse thrust to stop as quickly as possible. You can feel the difference in your body, that strong deceleration pressing you forward against your seatbelt. There's also something called idle reverse, where the engines redirect thrust, but at lower power. This is used during taxi in some situations, helping the plane back up from the gate without needing a tug vehicle, though many airlines avoid this because it can blow debris around the ramp area. Once the plane slows below about 60 or 70 miles per hour, the thrust reversers close and stow back into their normal position. At lower speeds, they're less effective, and the wheel brakes take over completely. The transition is smooth but noticeable. That roar fades away, and the plane settles into a quiet roll toward the taxiway. But before any of this happens, before engines roar or wings lift or wheels touch ground, someone has to decide where this metal bird will fly. And that brings us to something few passengers ever see: an invisible structure that fills the entire sky above us. The sky isn't empty space where planes go wherever they want. It's filled with invisible highways, precisely mapped routes that crisscross the globe at different altitudes. These airways have names, rules, speed limits. Air traffic controllers watch every plane, keeping them separated by at least 5 miles horizontally or 1,000 feet vertically. Think of it like roads in the sky. Victor airways for lower altitudes, jet routes for higher ones. Each has a designation, a series of waypoints that planes follow like connect the dots. V12 or J584 coordinates in space that only exist as numbers in a computer, but are as real to pilots as the painted lines on a highway. Planes file flight plans that specify exactly which airways they'll use, what altitude they'll fly, and when they expect to reach each waypoint. Air traffic control divides the sky into sectors, each managed by a different controller. As your plane crosses from one sector to another, the pilot switches radio frequencies, checking in with the new controller. The handoff is seamless. One controller passes the plane to the next like runners passing a baton. At any given moment, someone is watching your plane on a radar screen, tracking its position, speed, and altitude. The controllers don't just watch, they give instructions. Climb to 37,000 feet. Turn left, heading 270. reduce speed to 250 knots. Every instruction is acknowledged by the pilot, read back word for word to confirm understanding. This constant communication keeps thousands of planes safely separated in a relatively small volume of sky. Separation is critical. 5 miles horizontally means if two planes are at the same altitude, they must be at least 5 miles apart. 1,000 feet vertically means if two planes are on the same route, one might fly at 35,000 feet, while another flies at 36,000 feet, just 1,000 feet away, but never at risk of collision. These standards have been refined over decades to balance safety with efficiency. Modern planes also talk to each other. A system called TCAS, Traffic Collision Avoidance System, allows planes to detect other aircraft nearby. If two planes get too close, TCAS alerts both pilots and tells them what to do. One plane gets a command to climb, the other to descend. The system works automatically, a backup to air traffic control that has prevented countless potential collisions. The airways aren't straight lines. They curve around restricted airspace, military zones, areas where planes aren't allowed to fly. They avoid major storm systems when possible. They're optimized for wind, taking advantage of jet streams when flying in the right direction, avoiding them when flying against the wind. Flight planners calculate the most efficient route before every flight, balancing distance, fuel consumption, and time. At night, if you look up at the right moment, you might see a plane's lights moving steadily across the sky. That plane is following one of these invisible roads, checking in with controllers, maintaining its assigned altitude and speed, surrounded by other planes you can't see, all moving through a carefully choreographed system that keeps everyone safe. All of this structure, all of this precision, and yet sometimes nature still surprises us, particularly when the plane hits something that shouldn't be there, something that appears without warning and makes the entire aircraft shake. Turbulence feels scary, but here's the truth. It's just rough air. The atmosphere isn't smooth. It's lumpy, choppy, filled with invisible currents and rivers of wind that flow in different directions at different speeds. When a plane crosses from one current to another, it bounces, like a boat on choppy water. The plane isn't in danger. It's designed to flex, to bend, to absorb these movements. Think of the atmosphere as an ocean, but made of air instead of water. In the ocean, you have waves, eddies, currents that swirl and mix. The atmosphere has the same thing. Warm air rises, cool air sinks. These movements create pockets of instability. When a plane flies through one of these pockets, it drops or rises suddenly. That's turbulence. Most turbulence comes from 3 sources. Thermal turbulence happens when the sun heats the ground unevenly. Hot air rises in columns, creating bumpy conditions at lower altitudes. This is why flights are often smoother at night or in the early morning, when the ground is cooler. Mechanical turbulence comes from wind flowing over mountains or buildings, creating waves and eddies downwind. And convective turbulence comes from thunderstorms, where powerful updrafts and downdrafts can move air at speeds of over 100 miles per hour. From inside the cabin, turbulence feels dramatic. The plane drops, your stomach lifts, bags rattle in the overhead bins. But to the plane itself, these movements are tiny. A drop that feels like 20 feet might actually be 2 or 3 feet. The plane's momentum is so enormous that even strong turbulence can't throw it around the way your body feels like it's being thrown. Airplane wings are tested to flex up and down by over 20 feet at the tips before they'd even begin to show signs of structural stress. During turbulence, they might move a few inches. The frame is built to handle forces far beyond anything weather can throw at it. Engineers test planes to destruction, bending wings until they break, just to know exactly where the limits are. Then, they design everything to operate well below those limits. Pilots have tools to predict and avoid the worst turbulence. Weather radar shows them where storms are building. Reports from other planes ahead on the same route warn them about rough patches. Flight planners route around known turbulent areas when possible. But some turbulence is unavoidable, and when it happens, the pilots simply slow the plane down to a specific speed called turbulence penetration speed, which minimizes stress on the airframe. That's why they turn the seatbelt sign on, not because the plane is in danger, but because people can get hurt if they're standing up or walking around. The plane stays firmly in the sky. The turbulence passes. Within minutes, the air smooths out again and the ride becomes calm. The safest thing to do during turbulence is the simplest thing. Stay seated. Keep your belt fastened. Let the plane do what it's designed to do. Flex, absorb, continue forward. But there's one type of turbulence that pilots actually can't see coming, and it's created by something completely invisible, hiding in perfectly clear skies. Sometimes turbulence strikes from perfectly clear skies. No clouds, no storms, no warning. This is clear air turbulence, caused by jet streams, those rivers of fast-moving air that circle the globe at high altitudes. When planes cross the boundary between calm air and a 200-mile-per-hour jet stream, they shake. Not because something's wrong, but because they just flew through an invisible wall of wind. Jet streams form where cold polar air meets warm tropical air. The temperature difference creates a boundary, and along that boundary, wind accelerates. These rivers of air flow from west to east, meandering north and south like a snake sliding across the planet. They're typically found at altitudes between 30,000 and 40,000 feet, exactly where passenger jets cruise. The wind speed inside a jet stream can reach 250 miles per hour. That's faster than most hurricanes. But it's not the speed itself that creates turbulence. It's the shear, the sudden change from slow air to fast air. Imagine swimming in a pool where half the water is standing still and half is rushing past at highway speeds. The boundary between them would churn and swirl. That's what happens in the air. Wind shear can be vertical or horizontal. Vertical shear means wind speed changes with altitude. Horizontal shear means it changes across distance at the same altitude. Both create instability. The atmosphere tries to smooth out these differences, creating rolling waves of turbulence that can extend for miles around a jet stream's core. Pilots can't see clear air turbulence on radar because there's nothing to reflect the radar signal. No moisture, no particles, just moving air. They rely on reports from other aircraft, forecasts from meteorologists, and their own experience reading weather patterns. When they know they're approaching a jet stream, they might adjust altitude to avoid the strongest winds or the roughest boundaries. Sometimes, airlines actually want to fly in jet streams. A tailwind of 150 miles per hour can cut flight time significantly and save thousands of gallons of fuel. Flights from Los Angeles to New York often ride the jet stream eastward, arriving 30 or 40 minutes early. But the return trip westward avoids the jet stream when possible, because fighting that headwind would cost too much time and fuel. The jet stream isn't constant. It shifts position daily, even hourly. In winter, it dips farther south, bringing cold air and storms with it. In summer, it retreats north. Climate patterns like El Niño can alter its path for months at a time. Pilots check its location and strength before every long flight, incorporating it into their route planning. There are actually multiple jet streams. The polar jet is the strongest, flowing at high latitudes. The subtropical jet flows closer to the equator at slightly lower altitudes. They can merge, split, or run parallel to each other. During certain weather patterns, they create complex wind fields that challenge even experienced pilots to navigate efficiently. All of this invisible structure, all of this atmospheric complexity, exists because of physics and temperature differences and Earth's rotation. And every flight, every journey happens because humans figured this out, because we learned to read the sky and work with it. But that learning took time, trial, and tragedy. All of this, every flight, every journey through invisible air currents and jet streams, happens because of something humans figured out barely a century ago. And the breakthrough wasn't what most people think. Most people believe the Wright brothers figured out how to make things fly. But humans already knew about lift. Kites flew, gliders flew. What the Wright brothers figured out was control. Before 1903, people had built flying machines that could leave the ground. Otto Lilienthal in Germany made over 2,000 flights in hang gliders. But he died when a gust of wind flipped his glider and he couldn't recover. Others crashed the same way. They could get airborne, but they couldn't steer, couldn't adjust to changing conditions, couldn't respond when the wind pushed them somewhere they didn't want to go. The Wright brothers solved this with wing warping. They discovered that by twisting the wings, they could control roll, the motion that tips one wing up and the other down. They added a movable rudder for yaw, turning left or right. And they put a movable elevator on the front for pitch, pointing the nose up or down. 3 axes of control, all working together. This was the revolution. Their first flight at Kitty Hawk lasted 12 seconds and covered 120 feet. Less distance than a modern jetliner's wingspan. But it was controlled flight. Orville Wright lifted off the ground, maintained altitude, and landed where he intended. That had never been done before with a heavier-than-air machine carrying a person. The genius was understanding that flight required constant adjustment. You couldn't just launch into the air and expect to stay stable. The atmosphere pushes and pulls. Gusts come from unexpected directions. Weight shifts as fuel burns. A flying machine needed to respond to all of this continuously, or it would tumble out of the sky. Modern airplanes still use the same 3-axis control system. Ailerons on the wings control roll. The rudder on the tail controls yaw. elevators on the horizontal stabilizer control pitch. These surfaces are larger and more sophisticated than the Wright brothers' design, but the principle is identical. Change the airflow over a control surface, and you change how the plane moves. Pilots use these controls constantly, even in smooth air. Small adjustments to maintain heading, altitude, speed. The plane wants to fly, but it doesn't want to fly straight and level without input. Every few seconds, the pilot or autopilot makes a tiny correction, banking slightly left to counter a crosswind, adjusting pitch to maintain altitude as weight decreases from fuel burn. It's a continuous dance with the air. The Wright brothers tested over 200 different wing designs before finding one that worked reliably. They built a wind tunnel to study how air flowed over different shapes. They kept detailed notes on every test flight, learning from each success and failure. Their methodical approach turned flying from a fantasy into an engineering problem that could be solved. Within 10 years of that first flight, planes were performing loops and rolls. Within 50 years, jets were breaking the sound barrier. Within 70 years, humans landed on the moon. The speed of progress was staggering, all built on the foundation of those 3-axis controls that let pilots actually fly where they wanted to go. That control system allows pilots to do something that seems impossible: land a plane they can barely see out of. When fog blankets an airport or clouds hang low, pilots don't need to see the runway. The plane follows invisible radio beams that guide it down, slope by slope, until the wheels are inches from the ground. The instruments show exactly where the plane is in 3-dimensional space, with such precision that it can land itself if needed. This system is called ILS, Instrument Landing System. It works with 2 radio beams transmitted from the airport. One beam, called the localizer, provides horizontal guidance. It tells the plane if it's left or right of the runway centerline. The other beam, called the glide slope, provides vertical guidance. It tells the plane if it's above or below the correct descent path. The localizer beam spreads out from the far end of the runway like a narrow cone. As the plane approaches, receivers on board detect the signal strength. If the plane drifts left, the left side of the beam becomes stronger. If it drifts right, the right side strengthens. The cockpit instruments translate this into a simple display: a needle that shows which way to turn to get back on centerline. The glide slope beam angles upward from near the runway threshold, typically at 3 degrees. That's the ideal descent angle, steep enough to clear obstacles, but gentle enough for a smooth landing. The plane's receivers detect whether it's above or below this beam, displaying another needle that tells the pilots whether to climb or descend. Following both beams simultaneously creates a precise path through the sky, a 3-dimensional corridor that leads straight to the touchdown zone. Even in conditions where visibility drops to a 1/4 mile or less, the plane can stay perfectly aligned with the runway, descending at the correct angle, until it breaks out of the clouds just seconds before landing. Modern systems can do even better. Category 3, ILS can guide a plane all the way to touchdown and rollout in 0 visibility. The autopilot follows the beams, makes the final adjustments, flares the nose up just before the wheels touch, and even steers the plane down the centerline after landing. Pilots monitor the instruments, ready to take over if something goes wrong. But the plane is essentially landing itself. There are also distance markers along the approach path. Radio beacons called the outer marker and middle marker tell the plane how far it is from the runway threshold. At the outer marker, typically 4 to 7 miles out, the plane should be fully configured for landing, with gear down and flaps extended. At the middle marker, about half a mile out, the plane should be on glide slope and just seconds from touchdown. Pilots train for instrument approaches constantly. They practice in simulators where visibility is reduced to nothing, following needles on a screen, trusting instruments over their own senses. Because sometimes what you feel and what the instruments show don't match. The instruments are always right. Your inner ear can be fooled by acceleration and banking, but radio beams don't lie. But what about all those lights you see blinking on the wings at night, cutting through the darkness as the plane descends through clouds toward an invisible runway? Every airplane speaks through lights. Red on the left wingtip, green on the right, white on the tail. At night, these lights tell other pilots which direction a plane is moving without saying a word. A green light approaching means that plane is moving right to left across your path. Red means left to right. Both visible together means it's coming straight at you. This system comes from maritime tradition. Ships have used the same red and green pattern for over a century. Port side red, starboard side green. Pilots adopted it because it works. Because in darkness or fog, color tells you instantly what you need to know. No radio call required, no computer system, just light and position and human recognition. The white tail light, called the position light, shines backward. If you see only white, that plane is moving away from you. No conflict. But if you see red and green together, both wings visible, that plane is heading toward you and you need to take action. These simple color rules have prevented countless mid-air collisions over the decades. There are other lights too. Strobe lights flash bright white, making the plane more visible from long distances. They flash several times per second, cutting through darkness and haze. Anti-collision lights, usually red beacons on top and bottom of the fuselage, rotate or flash to make the plane visible from all angles. Landing lights, incredibly bright white beams, illuminate the runway during approach and takeoff. Pilots turn these lights on and off, following specific rules. Strobes go on before entering an active runway. Landing lights come on below 10,000 feet. Position lights stay on whenever the engines are running. Each light serves a purpose, and other pilots know what those lights mean. It's a silent language that everyone in aviation speaks. At night from the ground, you can identify a plane by its lights. The red and green wingtip lights blink steadily. The white strobe flashes bright. The red beacon rotates. Together, they create a distinct pattern, different from stars or satellites or anything else in the sky. Once you know what to look for, you can't unsee it. There's something peaceful about watching planes at night, seeing those lights move across the sky in their invisible highways. Each set of lights is hundreds of people traveling somewhere, trusting these systems to keep them safe. And the lights do their job, marking position and direction, communicating without words. Some airports have approach lighting systems that extend thousands of feet from the runway threshold. Rows of lights create a visual path for pilots on final approach, especially helpful when breaking out of clouds at low altitude. The pattern shows not just where the runway is, but also the correct angle of descent. Too high and you're looking down at the lights. Too low and they're above you. On the correct glide slope, the lights form a straight line leading to the threshold. All of these signals, all of this communication through light and color, happens in a substance most people never think about. We treat air like nothing, like empty space. But it's not empty. It's an ocean, and we're swimming through it. We think of air as nothing, as empty space. But it's not. Air is a fluid, just like water. Thinner, yes, but still a substance you move through. Planes don't fly over air, they swim through it. Wings push it down, engines push it back, and the plane moves forward because air is something real, something physical, something with weight and pressure and movement. A cubic yard of air at sea level weighs about 2 pounds. That doesn't sound like much until you think about scale. The atmosphere above 1 square mile of ground weighs about 14 million tons. All that weight pressing down creates pressure. And that pressure is what holds you to the ground, what makes weather, what allows flight to work. When you move through air, you push it aside. It has to go somewhere. Most flows around you, over and under and to the sides, but some gets compressed in front of you, creating a zone of higher pressure. This compression takes energy, which is why it's harder to ride a bicycle fast than slow. You're pushing against air resistance, forcing air molecules out of your path. Planes do the same thing, but at a scale that's hard to imagine. A 747 at cruising speed displaces over 1,000 cubic feet of air every second. That air has to move. It flows over the wings, around the fuselage, past the engines. The faster the plane moves, the more air it has to push aside, and the more resistance it encounters. This is why planes need such powerful engines. They're not just lifting the plane, they're constantly shoving air out of the way. But air isn't just resistant, it's also supportive. Those wings we talked about earlier work because air has substance. When the wing deflects air downward, that air pushes back, lifting the wing upward. Without air having mass and momentum, this wouldn't work. The wing would slice through vacuum and generate no lift at all. Air also carries information. Sound waves are vibrations traveling through air molecules. When the jet engines roar, they're compressing and expanding the air thousands of times per second, creating pressure waves that spread outward. Those waves reach your ears and you perceive them as sound. In space, in vacuum, those engines would be silent because there's no air to carry the vibrations. Temperature affects how air behaves. Hot air is less dense than cold air. The molecules spread farther apart, making the air lighter and thinner. This is why planes take longer to take off on hot days. The wings need to move faster through thin air to generate the same amount of lift. On cold days, the denser air provides more lift at lower speeds, letting planes take off on shorter runways. Humidity matters too. Water vapor is actually lighter than dry air, molecule for molecule. So humid air is less dense than dry air at the same temperature. This seems backward because rain is heavy. but individual water molecules weigh less than nitrogen or oxygen molecules. On hot, humid days, air is at its thinnest, and plane performance suffers the most. And that ocean of air does something remarkable to the human body when you're floating through it at 35,000 feet. Changes so subtle, you barely notice them happening. At 35,000 feet, even with cabin pressure, you're effectively at about 6,000 to 8,000 feet elevation. Your blood carries slightly less oxygen. Your sense of taste dulls by about 30%, which is why airplane food seems bland. You get dehydrated faster because the air inside the cabin has less moisture than a desert. Your body is quietly adapting to being somewhere humans weren't meant to be. The oxygen thing is subtle but real. At 8,000 feet equivalent altitude, the air pressure is lower, so each breath delivers about 25% less oxygen than at sea level. Your body compensates by breathing slightly faster and deeper, though you probably won't notice. Your heart rate increases a bit. Red blood cells work harder to grab oxygen molecules from the thin air in your lungs. Most people handle this fine. But if you already have breathing problems, or heart conditions, or you're anemic, that 25% reduction can make you feel tired or short of breath. This is why flight attendants carry portable oxygen bottles, and why some passengers with medical conditions arrange for supplemental oxygen before flying. The taste thing happens because smell and taste are connected, and your nasal passages dry out in the low humidity cabin. The air inside a plane typically has about 10 to 20% humidity, drier than most deserts. Your mucous membranes, which help you smell, stop working as well when they dry out. Food loses its flavor. This is why airlines oversalt and overseason meals. They're compensating for your diminished sense of taste. Dehydration sneaks up on you. That dry air pulls moisture from your skin, your lungs, your eyes. Every breath out carries water vapor that isn't replaced by water vapor in the air you breathe in. Over a long flight, you can lose a significant amount of water without realizing it. This is why flight attendants constantly offer water, why you should drink more than you think you need, why you might arrive feeling tired and foggy even though you were just sitting. Your ears pop because of pressure changes. As the plane climbs, cabin pressure decreases. The air inside your middle ear, trapped behind your eardrum, expands. Eventually, the pressure difference forces the eustachian tube to open, equalizing the pressure with a pop. On descent, the reverse happens. External pressure increases, compressing the air in your middle ear until you equalize again. Some people's eustachian tubes don't equalize easily. The pressure builds, causing pain or temporary hearing loss. Swallowing, yawning, or pinching your nose and gently blowing can help. The pop you feel is literally air moving through a small tube in your head, balancing pressure between inside and outside. Your feet and ankles might swell slightly. Reduced cabin pressure allows the fluids in your body to expand a bit. Sitting still for hours reduces circulation. Blood pools in your lower legs. This combination leads to that tight feeling in your shoes by the end of a long flight. Walking around helps. Flexing your feet and calves helps. Compression socks help, but some swelling is normal and harmless. But there's something else your body does at altitude that airlines actually design around. Something that affects every passenger, whether they realize it or not. As the plane climbs, and cabin pressure drops slightly, the gases inside your body expand. The air in your intestines, your stomach, your sinuses. Everything puffs up a little, not dangerously, but noticeably. This is why you feel bloated, why your ears pop, why that sealed bag of chips becomes a tight little balloon. The physics is simple. At lower pressure, gas molecules spread out. They want more space. The gas in your digestive system, produced by normal digestion and swallowing air, occupies maybe a cup's worth of volume on the ground. At cruising altitude, that same gas expands by about 25%. Now it's taking up more room, pressing against your intestinal walls, creating that uncomfortable full feeling. This affects everyone, but some people feel it more than others. If you ate beans or broccoli or other gas-producing foods before flying, you'll have more gas to expand. If you drank carbonated beverages, you've added extra gas to your stomach. Even chewing gum makes it worse, because you swallow air with each chew. The expansion happens gradually as the plane climbs. Most people don't notice until they're at cruising altitude and suddenly realize they feel uncomfortably full. The reverse happens on descent, but by then you've probably generated even more gas through digestion, so the relief isn't as noticeable. This is also why airlines tell you to avoid certain foods before flying, especially on long flights. Cabbage, onions, carbonated drinks, anything that produces gas. It's not just about the smell, though that's certainly a consideration in a closed space with recycled air. It's about passenger comfort. Airlines know that bloated, uncomfortable passengers complain more and enjoy the flight less. That chip bag phenomenon is the same principle, but more visible. The bag was sealed at ground level pressure, trapping air inside. As the plane climbs, that trapped air expands. The bag puffs up like a balloon, sometimes to the point where it feels like it might burst. On descent, it deflates again. Some passengers use this as an informal altitude indicator, watching their snack bags swell and shrink. The same thing happens in closed bottles. A water bottle filled and capped at sea level will crackle and deform as the plane climbs. The pressure inside pushing outward against the lower pressure outside. Open the cap and you hear a hiss as the pressure equalizes. On descent, the bottle crinkles inward as the higher external pressure squeezes it. Your sinuses go through the same process. If you have a cold or allergies and your sinuses are blocked, the trapped air can't equalize. The pressure builds as the plane climbs, causing pain and sometimes intense headaches. This is why doctors recommend not flying with severe congestion. The pressure difference can even rupture eardrums if the eustachian tubes are completely blocked. Flight attendants see all of this constantly. They know passengers will be uncomfortable. They know to offer water frequently, to keep carbonated drinks limited, to not be surprised when everyone seems gassy. It's just physics, acting on biology in an environment we didn't evolve for. All of these tiny discomforts exist because the plane is maintaining a delicate balance, holding back the massive pressure difference between inside and outside. The cabin is essentially a sealed tube, pressurized like a balloon. Air is constantly being pumped in from the engines and released in controlled amounts through tiny valves. The plane's skin is holding back the difference between the thick air inside and the thin air outside. If that seal broke suddenly, everything not strapped down would be sucked toward the breach. But this is incredibly rare because the plane is designed with multiple redundancies. Think about what's happening structurally. At 35,000 feet, the pressure outside is about 3.5 pounds per square inch. Inside the cabin, it's maintained at around 11 pounds per square inch. That's a difference of 7.5 pounds pressing outward on every single square inch of the fuselage. On a large plane, that adds up to hundreds of thousands of pounds of force trying to push the walls outward. The fuselage is designed as a pressure vessel, similar to a scuba tank or a propane cylinder. It's cylindrical because circles distribute stress evenly, no corners to concentrate force. The aluminum skin is thick enough and strong enough to handle this pressure difference thousands of times over the life of the aircraft. It's tested repeatedly, flexed and pressurized in factories until engineers know exactly how much it can take. The windows are the weak points, or they would be if they weren't so carefully engineered. Each window is actually multiple layers of acrylic, not glass. The innermost pane holds the pressure. The outer layers are backups and protect against scratches and impacts. The windows are slightly oval, not rectangular, because rounded shapes handle pressure better than sharp corners. Air comes into the cabin from the engines through a system of pipes and valves. Bleed air from the compressor section is cooled down, mixed to the right temperature, and distributed throughout the cabin. Meanwhile, outflow valves at the rear of the plane release air at a controlled rate. The balance between incoming and outgoing air maintains the desired cabin pressure. Those outflow valves are automatic. Computers monitor cabin pressure constantly and adjust the valves to maintain the correct level. As the plane climbs, the valves close gradually, letting less air escape so pressure can build up inside. As the plane descends, the valves open gradually, letting cabin pressure increase to match the outside pressure by the time the plane lands. If something went wrong, if a door seal failed or a window cracked, the cabin would depressurize. Not explosively in most cases, but rapidly. The air would rush out through the breach, and pressure would drop to match the outside atmosphere within seconds. This is why oxygen masks drop from overhead compartments. They give passengers time to breathe, while the pilots descend to a safer altitude, where the air is thick enough to sustain life. The pilots would immediately start an emergency descent, diving toward 10,000 feet as fast as the plane can safely descend. At that altitude, people can breathe without supplemental oxygen. The entire emergency would last maybe 3 or 4 minutes, from depressurization to reaching breathable air. But this almost never happens. The pressurization system is one of the most reliable systems on the aircraft. And those redundancies extend to something most passengers never notice: backups built into every critical system. Every critical system on an airplane has a backup, and that backup has a backup. Engines, hydraulics, electrical systems, computers, even the pilots themselves. The plane can lose an engine and fly fine. It can lose multiple systems and still land safely. This redundancy is why flying is statistically the safest form of travel humans have ever invented. Start with the engines. Commercial jets have at least 2, most have 4. Each engine alone can keep the plane airborne. If one fails, the other takes over. The plane can't climb as steeply and might need to fly at a lower altitude, but it stays in the air. Pilots train for engine failures constantly. It's one of the most practiced emergency procedures. Losing an engine is serious but manageable. Hydraulics power almost everything on a plane: flight controls, landing gear, brakes, flaps. There are typically 3 independent hydraulic systems, each with its own pumps and fluid reservoirs. If one system fails, the other 2 keep working. Some planes have a 4th backup system powered by a ram air turbine, a small propeller that drops into the airstream and generates power from the wind. Electrical systems are tripled too. Generators on each engine produce electricity. If those fail, an auxiliary power unit in the tail can generate power. If that fails, batteries take over. The batteries alone can power essential systems for 30 minutes or more, enough time to land safely. Some planes also have that ram air turbine for generating emergency electrical power. Even the pilots are redundancy. The captain and first officer both know how to fly the plane. Both are fully qualified. If one becomes incapacitated, the other takes over. They also cross-check each other constantly, calling out actions and confirming decisions. 2 sets of eyes, 2 brains, catching mistakes before they become problems. The flight computers are redundant. Modern airliners have multiple flight management computers running simultaneously, comparing their outputs. If one computer gives a different answer than the others, it's ignored. The system votes, essentially, and the majority wins. This prevents a single computer glitch from causing problems. Navigation systems are layered. GPS is primary, but inertial navigation systems provide backup. Those systems use gyroscopes and accelerometers to track the plane's position by measuring every turn and speed change. They don't need any external signal. Radio navigation beacons provide another layer. Even if all electronic navigation failed, pilots could navigate by compass and landmarks. Communication systems multiply too. Multiple radios, multiple frequencies. If one radio fails, there are others. If radio fails completely, there are backup emergency frequencies monitored worldwide. Transponders send position data to air traffic control. If the main transponder fails, there's a backup. Some planes have satellite communication as an additional layer. Landing gear has mechanical backups. If hydraulics fail, gravity can drop the gear. Pins and locks hold it in place without power. The wheels themselves have multiple brakes, multiple systems to slow the plane on the ground. Anti-skid systems prevent lockups, but even if those fail, the brakes still work mechanically. This philosophy of redundancy is built into every aspect of aircraft design. Engineers assume things will fail. They design around those failures. The question isn't whether something might break, but whether the plane can still operate safely when it does. But even with all these safety systems, there's one thing planes can't fully control. One force of nature that demands respect and careful navigation. Pilots don't fly through thunderstorms. They fly around them. Modern radar shows weather patterns hundreds of miles ahead, allowing pilots to adjust course early, to find the smooth air between the chaos. Lightning strikes planes occasionally, but the metal skin conducts the electricity harmlessly around the passengers and out through static discharge wicks on the trailing edges of wings and tail. Weather radar works by sending out radio pulses and measuring what bounces back. Water droplets reflect the signal. The bigger and denser the droplets, the stronger the return. Heavy rain shows up bright on the radar display. The system can even detect turbulence by measuring how much the raindrops are moving around inside the clouds. Calm rain appears smooth. Violent updrafts and downdrafts create a chaotic, shifting pattern that the radar interprets as severe turbulence. Thunderstorms are massive engines of energy. Updrafts inside them can exceed 100 miles per hour, strong enough to carry a small plane vertically against its will. Downdrafts are equally powerful, pushing planes toward the ground with tremendous force. Hail forms in these updrafts, carried high into the atmosphere where it freezes, then falls, then gets carried up again, adding layers of ice with each cycle until it's heavy enough to fall to the ground. Pilots give thunderstorms a wide berth. 20 miles is standard clearance from the most intense parts. The clouds themselves can tower to 50,000 feet or higher, well above any plane's cruising altitude. The turbulence extends beyond the visible cloud boundaries, sometimes reaching clear air miles away from the storm itself. Lightning doesn't hurt the plane. The metal skin is a Faraday cage, conducting electricity around the outside without letting it penetrate to the interior. Passengers might see a bright flash, hear a loud bang, but the plane continues flying normally. After landing, maintenance crews inspect for any burn marks or small pits where the lightning entered and exited, but structural damage is virtually non-existent. Those static discharge wicks on the trailing edges of wings and tail are there to help the plane shed built-up static electricity gradually. As the plane flies through air, friction creates electrical charge. Without a way to release it, that charge would build up and eventually discharge all at once, potentially interfering with communication or navigation systems. The wicks bleed off the charge continuously in tiny sparks too small to see or hear. Ice is another weather hazard. Supercooled water droplets in clouds can freeze instantly when they hit the plane's surface, building up layers of ice on wings, engines, and sensors. Ice changes the wing's shape, disrupting airflow and reducing lift. It can block engine intakes or clog pitot tubes that measure airspeed. So, planes have de-icing systems. Hot air from the engines flows through channels in the wings. Electrical heating elements warm sensor probes. Rubber boots on the wing, leading edges inflate and deflate, cracking ice off before it can accumulate. Pilots check weather forecasts constantly, before the flight and during it. They communicate with other planes ahead on the same route, asking about conditions. They work with dispatchers on the ground who have access to even more detailed weather data. The goal is always to find the smoothest path, to avoid the worst of what nature throws at them. All of this technology, all of this precision, serves one simple purpose, a goal so routine we've forgotten how extraordinary it is. Think about what's actually happening. Hundreds of tons of metal, fuel, and people accelerate down a strip of pavement until they're moving fast enough that air itself holds them up. They climb 6 miles into an atmosphere that would kill an unprotected human in minutes. They hurtle through that hostile environment at nearly the speed of sound. And then they descend gracefully back to Earth, touching down so gently that passengers barely notice. This happens tens of thousands of times every day, and it's so routine we complain about the snacks. Every single flight is a controlled fall, a continuous balance between thrust and drag, lift and weight. Stop the engines and the plane becomes a glider, still flyable but descending. Stop moving forward and the wings lose lift and the plane drops. The whole operation exists in a narrow window of physics that has to be maintained every second from takeoff to landing. Consider the coordination required. The pilots fly the plane, but dozens of people contribute to each flight. Dispatchers plan the route. Meteorologists forecast weather. Mechanics inspect every system. Fuel trucks fill the tanks precisely, calculating weight and balance. Baggage handlers load cargo in specific positions to keep the center of gravity correct. Air traffic controllers guide the plane through crowded skies. All of these people, working together, making one flight possible. And it works. The fatal accident rate for commercial aviation in developed countries is about 1 per 10 million flights. You could fly every day for 27,000 years before statistically experiencing a fatal crash. Driving to the airport is more dangerous than the flight itself. This level of safety is unprecedented in human history, achieved through engineering, training, regulation, and constant improvement. Every accident is studied exhaustively. Investigators recover the wreckage, examine every piece, analyze flight data and voice recordings. They figure out exactly what went wrong. Then, the entire industry learns from it. Regulations change, training improves, designs are modified. The same mistake never causes another crash. This feedback loop has made flying safer every decade. The technology keeps advancing. Modern planes have sensors monitoring thousands of parameters continuously. Computers analyze the data, predicting maintenance needs before anything breaks. Composite materials make planes lighter and stronger. More efficient engines reduce fuel consumption and emissions. Satellite navigation provides precision that was impossible 20 years ago. Yet the fundamentals remain. Wings generating lift, engines creating thrust, control surfaces adjusting attitude. The Wright brothers would recognize these principles, even if the execution has evolved beyond anything they could have imagined. We've taken their basic insights and refined them through a century of learning, building planes that carry millions of people safely across oceans and continents. And we take it for granted. We board a plane, stow our bags, sit down, and expect to arrive safely at our destination hours later. We get annoyed if the flight is delayed. We complain about legroom. We barely glance out the window at the impossible view below. We've become so accustomed to this miracle that we've forgotten it's miraculous. But every flight is an achievement. Every safe landing is a success story. Every time a plane lifts off, humans are temporarily defeating gravity, moving through an element we weren't built for, doing something that should be impossible. Which brings us back to where we started, to you, sitting here, thinking about all those planes above. Right now, as you listen to this, there are roughly 10,000 planes in the air. 1 million people suspended between ground and space, reading, sleeping, thinking, dreaming. Each one of those flights is a small miracle, a triumph of human curiosity and engineering. And every time you see a plane cutting across the sky, leaving a white trail behind it, you're watching something impossible made ordinary through understanding. Those white trails, called contrails, are ice crystals. At high altitude, the water vapor in jet exhaust freezes instantly in the cold air, creating artificial clouds that can stretch for miles. They mark the invisible highways we talked about earlier, writing temporary roads across the sky. Some days, the trails persist for hours, spreading and thinning. Other days, they vanish almost immediately. It depends on humidity and temperature at that altitude, factors constantly shifting with the weather. The sky above you is always full of metal birds and invisible highways, full of people traveling and returning home, full of physics made practical and danger made safe. Somewhere up there right now, someone is taking their first flight, nervous and excited. Someone else is coming home after years away. A couple is heading toward their wedding. A business person is rushing to a meeting. A family is starting a vacation. All of them floating through thin air, trusting systems they don't understand, arriving safely because thousands of people built something reliable. Flight connects the world in ways previous generations couldn't imagine. You can have breakfast in New York and dinner in London. You can watch the sunset over the Pacific and the sunrise over Asia within 24 hours. The planet has become smaller, not in size, but in the time it takes to cross it. This has changed everything about how humans live, work, and relate to each other. And it all started with two bicycle mechanics who wondered if they could control a glider. Within one lifetime, humans went from that 12-second flight at Kitty Hawk to jets carrying hundreds of people across oceans. Within 2 lifetimes, we landed on the moon. The pace of progress is staggering when you step back and look at it. Now, as you drift towards sleep, you carry this knowledge with you. Flight isn't magic, it's something better. It's humans figuring out how to do something we were never built to do, and doing it so well that we take it for granted. It's physics and engineering and training and redundancy and constant improvement. It's thousands of people working together to move millions of others safely through the sky. The next time you're on a plane, maybe you'll think about the air being pumped in from the engines, the pressure being maintained by automatic valves, the wings flexing slightly in turbulence, the invisible jet streams flowing overhead. Maybe you'll appreciate the complexity that makes it seem simple. If this journey through the science of flight brought you peace, consider hitting that like button and subscribing for more quiet explorations. Leave a comment about your favorite flying moment, or tell me where you're listening from. Tomorrow we'll drift somewhere new together, but for now, rest well. Let these facts settle gently in your mind, like a plane touching down after a long flight. Close your eyes, breathe slowly, and dream of floating through endless sky. Good night.